before I forget. Okay, so for the second workshop, if you've been on the stream site and looked at the workshop worksheet, you would have noticed that the second workshop is pretty much very exploratory, using the moving man FET simulation. You will be looking at the relationships between position, velocity, and acceleration, and how these are, what does positive and negative mean, and all of that. So I think I would like to start the workshop by discussing a little bit about the labs, because you might know the weekend is coming up and some of you might want to take advantage of the weekend to look at the first lab. So I will, the video introduction for the first lab is actually already on stream. So I will not repeat what Tony said in his video, but I just would like to point out some things that you might find useful when you're doing the homework for the first lab. So in the first lab, okay. So I hope you can see that screen okay. So the first lab, in this lab, you will investigate uncertainties. Investigate uncertainties. Ooh, that's too thick. And when you measure, by measuring your distance and your time and figuring out your average speed. So when you measure something, there is a natural variability in your measurement. So say you measure, so we've learned that average speed is distance over time. So when you measure, for example, your distance, measure it 2 times, you'll find that there's some sort of variability in your measurements. Maybe in your first measurement, it was 1 meter, and then your second measurement is 1.01 meters. So in any measurement that we make, there is this natural variability in our measurements. And so that's where uncertainty comes in. Uncertainty measures how well the equipment and method can measure as close to the true value as possible. So that's what you will be investigating in this lab. The tasks here, you'll see that there's a first part. The tasks here will ask you to measure the distance and the time for a ball that you've thrown. So this ones, you don't have to submit your answers for the tasks. The role of the task is sort of like a practice for you to sort of understand what uncertainties is and what's going on in the lab in this experiment. So the tasks are guided activities that you can do to understand what's going on before you do your homework. So these are guided. So you're free to answer these questions as you go along in the task and also the discussions. It gets you thinking about what you'll do for your homework. So there are Kahoot questions, and we can look at the answers to these questions later on, because the answers are not in the video introduction. But essentially, this is what you will need to submit, the homework here, that this is what you'll need to submit before the 20th of March. And here you will be asked to design and execute a plan for measuring your average walking speed. So for this homework, you really just need a stopwatch. You can use the regular stopwatch or the stopwatch on your phone, and a measuring device, like a tape measure, or yeah, I know some phones can measure also the distance, or some smart watches can also measure the distance. You can also use that instrument, but um, remember that even if you use those accurate measuring devices, there will always be some uncertainty or some variability in your um, average walking speed. So for you to find the uncertainty, the variability in your measurements, how many times do you think you should repeat your measurement? You think one measurement for your distance and one measurement for the time, is that sufficient? Or do you think you need to take multiple measurements? So obviously, if you take just one measurement of your distance and one measurement of your time, sure, you'll get your average speed, but there's no way of knowing how good your measurement is. So ensure that you make several measurements, so at least 3. Yeah, at least 3 would be good, maybe around 5 or 6. Don't go less than 3, because 2 measurements, they're a bit also inconclusive if you only have 2 measurements. So at least 3, that you're right, Liza. 4, 5 or 6 measurements would be good. Then you can see your natural variability in the speed. So that's where you put your raw data here. So in the description of the experiment, it doesn't have to be very long. You can just say, I walked this particular distance. I measured that distance using a tape measure or whatever you use. And then I timed the time it took me to cover this distance using a stopwatch or whatever measurement you use. And that should be okay. That should be sufficient for describing your experiment. And that one, you'll see a marking rubric here. So if you've described sufficiently, how you measured your distance and how you measured your time, that should give you a tick for the good, give you full marks essentially for that part. And then please write down your raw data. So if you've taken, say, 5 measurements of your distance, okay, then please put down, for example, distance 1, distance 2, and so on. Put your raw data here. Also, write down the times for those particular distances. I need to see that in order to verify whether your calculation for the speed is correct. So once you have your raw data there, then you should have full marks for the second criteria, sufficient data collected. Of course, if you've only put one measurement there, that's not sufficient, right? So I will need to see multiple measurements. And then you can calculate your speed for each distance and time information, and you can write them down there, or you can write down, here, your average walking speed for each of your measurements, and that should be sufficient for getting full marks for the next criteria. And then estimate the uncertainty. Sort of, you can look at your average speeds and a certain, like, say, how confident am I? So what's the variability in my speed? Maybe your speed ranges over, there's a difference of 0.1 meter per second or whatever. And that's what you put as your estimated uncertainty. And that should give you full marks for that criteria as well. It also, in the video, it also asks you to compare your work with another person's work. That can become a little bit tricky because we're all like doing this in distance mode, and we're not, we haven't met anyone face-to-face in our class. I would suggest maybe there's these Albany Student Association has a program called Class Advocate or Class Representative. If any one of you wants to be the class advocate or class representative, please feel free to volunteer for that. After the lecture, I'll put out an announcement on stream about class advocates, and if you're interested, you can volunteer for that. In previous years, the class advocates sort of organized, for example, a Facebook group or a WhatsApp group, and that's where you can talk amongst yourselves and say, let's share information about your lab results. Because it's not just in this first lab where we will be asking you to compare your results with another person's. So it will be useful to sort of have that group. Otherwise, you can also just go onto stream in the stream forums and sort of interact with each other there and share data for the labs, because you will need to compare your lab results with other people, right? So that's sort of what you need to do for the first lab. And as I've said, if you need more detailed information about this lab, then you can head over to the stream site and watch the video. But we can look at the answers to the Kahoot questions. So if you've been at school maybe in the last 5 or 6 years, you'll be familiar with Kahoot. So let's look at the Kahoot questions, and because these questions are not answered in the video, these questions are sort of asking about what uncertainty is. So let's look at the questions. Yeah, if you can get out your device and you can just go to kahoot.it. Yeah, just go to this kahoot.it and enter this game pin. And just put like any nickname because I realize it's good. Wait a couple more seconds. Right. Let's go to kahoot.it, and then it will ask you to enter your game pin. So enter this 2656607 number, and then you should be able to access the Kahoot, right? Which will start in 5 seconds. So last chance to join. 5, 4, 3, 2, 1. Okay, right. Let's start. Okay, what is measurement uncertainty? Yeah. Okay, so it seems like most of the answers there for uncertainty is the result of a human error in the measurement process. This will really just result human error in the measurement process will really just result to a wrong value, um, a value that's very different from the actual value. And if you repeat your measurement, then all your measurements will actually be wrong. Like, say, an example of a human error would be like um, clicking the stopwatch when you've already walked a certain distance, right? Then that, even if you repeat it with that same method, with that same process, then all your measurements would be wrong. So it doesn't really give you a variability in your measurements. Human error does not really give you a variability in your measurements. Human error will give you a wrong result in your measurement. So uncertainty is more of the capability of the measurement method and the equipment. So it involves two factors. Your measurement method should be accurate enough, and the equipment that you use. So if you're using a very crude equipment, say you're measuring the time it took you to walk by just counting in your head, that's a very crude measurement method, then you'll have a very big variability in the measurements, a very big uncertainty. Right, so the answer, so uncertainty is more of the capability of the measurement method and the equipment. So the answer A, spread in the measured values due to faulty design or broken equipment, it's similar to human error, right? Because if you're using a broken stopwatch, then the time you're getting is actually wrong. So it's not, yeah, so it's not really related to the uncertainty. Okay, a broken measurement, broken equipment will give you a wrong measurement. And the last choice, a range of the experimental results, that's essentially similar to A. Range means spread. Yeah, so really uncertainty is the capability of the measurement method in the equipment. Okay, so next question. Oh, let's look at the scoreboard. Yay, very good. Have the Keelan in the lead. Okay, and the next question, question 2. Okay, right. So which of the following sources, in your opinion, contributed the most to your uncertainty? Okay. So we see most of the answers there is limitations of equipment. So so think that that's one factor. So when you're measuring something, um, that's one, the resolution of your limitation for your equipment is one thing, because as I used that as an example earlier, if you're using a measurement equipment that's very crude, then that will give you a large uncertainty. But it's also relating to the method for which you measured something. So the sources of your uncertainty can come from two things: the limitation of your instrument plus the limitation of your method. So that will fall into the limitation of the process for which you did your measurement. And so the correct answer there will be limitation of the measurement process. And the process involves the equipment as well as your the method, the reaction time, for example. Right? Yeah. So uncertainty in measuring distance is not correct, because it's distance is just one aspect. You still also need to consider time. So uncertainty, it's both the equipment and the method. It's the whole process of doing the measurement that contributes to the uncertainty. Okay. All right. So let's see the leaderboard. Oh, what happened? We didn't see. It skipped. Okay, let's just go now to question 3 because it skipped there. Estimate the uncertainty introduced due to the equipment. I think here, yeah, talking about the uncertainty in time, because it's in milliseconds. The choices are in milliseconds. So uncertainty in the equipment for measuring time. Yeah. All right. So most of you answered 0. Millisecond range. So there's some also answered less than 0.1 milliseconds and 1 to 100 milliseconds. So any answer within the millisecond range is correct. Okay. So the 0.1 to 1 milliseconds, less than 0.1 milliseconds, and 1 to 100 milliseconds, they're all correct because it depends on the resolution of your stopwatch. Okay, so some stopwatches can measure up to less than 0.1 milliseconds. So it depends on your measuring equipment. 0.1 to 1 seconds, I would say, is very crude. That would be like counting in your head, which is probably sensible, that it's not a sensible way of measuring your time. So time would usually have a small uncertainty in the millisecond range. All right, so let's look at the leaderboard. Hopefully it won't skip this time. Oh, why is it? It's so strange. We don't know who's leading. But now the fourth question. Estimate the uncertainty due to the measurement process. So the process includes now the equipment and the method, how you measure it. Right. Okay. Yeah. Here probably most of you now answered millisecond range. Probably thinking about the uncertainty introduced by the stopwatch being in the millisecond range. But here it's now the measurement process. So it includes now your reaction time. as well as yeah, your reaction time. And typically the reaction time is in the second range. So that's okay. It's probably not a very common information that we will know off the top of our head. So when we say measurement process, sure, it's in millisecond range if you only consider the resolution of your stopwatch that you're using. But if you're considering as well your reaction time, like Keelan said, about 1 second, 1 to 3 seconds would be a sensible reaction time. Then that limits the accuracy of your measurements as well. So if you're considering the measurement process and you're taking into account your reaction time, then the uncertainty would be around in the second range, between 1 to 10 seconds. Yeah. So some things to distinguish. Measurement process includes your instrument plus other things like reaction time. Measurement instrument, it's just the resolution or how accurate your measuring device is. Right? And oh, I don't know why it's skipping the little board now. And this is the last question, which contributed the most to your uncertainty. Yay. Okay, so now most of you answered limitations of the measured process, because then you have the reaction time there that most likely will contribute the most uncertainty in the overall speed that you will measure. Right, good. Okay, let's see if yeah, at least it will show us the overall winner. Yay! Congratulations, Nikita. And then Oksana. Oh, no, Nikita is third, Oksana, and then Hilan. Okay. All right. Good. So hopefully you've gained a little bit more understanding about what you're supposed to do with Lab 1 and uncertainties. Let me just stop this copy now. And I think there's a question in the chat. So do we just need to submit that one homework page and not all the others? Yes, that's right. You'll only need to submit that one homework page. In fact, you will be asked to enter your answers on stream directly. There are text boxes there, and Tony has set a word limit of 250 words. So yeah, so you don't really need very long explanations. For example, describing your method. As I've said earlier, you can just say, I measured my distance by using this equipment. I measured my time using this equipment, and then I calculated my average speed by dividing my distance with the time. So yeah, keep it brief and concise but clear. And then yeah, just enter your answers onto the stream site for just that single homework page. No need to submit your answers for the tasks, because that's for your practice. All right, any other questions about the lab? So I realize we're running out of time now. Yeah, so for the workshop is mostly exploratory. The second part, at least, you need to access this Running Man simulation, the one I showed you earlier, this Moving Man simulation. This is where you can play around with, for example, positive positions or negative positions, and just go through these the steps. It's sort of guiding you. The steps are sort of guiding you on what to do with the moving man simulation, and then asking your observations while you're doing those movements in the simulation. So you can do this. It's an exploratory workshop. So I think I'll let you do that, because there will be different answers for different people. So I think it doesn't make sense to discuss specific solutions to the questions. But maybe we can just look at this first part, because this is more concrete. The questions here are more concrete. So here we're given a motion diagram, and we want to determine which motion diagram corresponds to these situations: constant speed, at rest, slowing down, and speeding up. So for the first situation, constant speed, which diagram do you think corresponds to an object that's moving at constant speed? Yeah, and yeah. So let me just clarify. I mean, in physics, when we say object, we sort of refer to everything as objects, even if these are moving people. I hope you don't get it the wrong way. I mean, of course, people are not objects, but just the terminology when we say in physics, when we say object, that refers to everything in general, things or living or non-living things. We refer to them as objects. It doesn't we don't mean anything negative by using that. It just simplifies the discussion. So yeah, so which objects moving at a constant speed? Yep, see, when we say it's moving at a constant speed, it means that the distance traveled is has regular intervals over the same period of time. So if you measure the distance traveled every 1 second, you will see that the distance is the same every 1 second. That's an indication that the object is moving at a constant speed. So right, correct. Constant speed refers to motion in C. Okay, how about the motion that corresponds to at rest? Yeah, at rest. So at rest, obviously, the object's not moving, it's just staying put. And none of the pictures show you an object that's just standing still. So you're correct, that's correct. At rest, none of the figures shown. Slowing down, which figure shows slowing down? So what happens when you're slowing down? When you're slowing down, the distance that you cover becomes smaller and smaller, right? So that's correct. Keelan and Nikita are correct. Slowing down is the motion in A, because as time goes on, the car is covering a smaller and smaller distance because it's slowing down. And speeding up is the opposite of slowing down. Yeah, so obviously that's when you're covering longer and longer distances as time goes on, because you're moving faster and faster. Good. Okay. Right. I think that's okay. That all makes sense. And then maybe finally we can look at, yeah, you'll do the simulation, but without doing the simulation, because here in question 2, without using the moving man simulation, try to sketch what the chart might look like when you are moving with constant velocity. So when you're moving at constant velocity, how would the position time graph look like how would the velocity time graph look like, and how would the acceleration time graph look like? So let me just label our graphs, because we said if you're doing graphs, you should put labels, position x in meters, time in seconds, velocity. Yeah, I'll do velocity next after we do position time. So as we've seen here in the first question, if you're moving with constant speed, then the distance you're covering is fixed for a fixed time interval, and that will give you this straight line graph. Okay. We've also seen in the lecture, if you have a straight line graph, the instantaneous velocity at each point will be the same, because the steepness of the tangent line at each point will be the same. Therefore, a straight line position time graph will give you a constant velocity. So when you draw your velocity time graph, velocity and the unit for velocity is meters per second and time units in seconds. The problem actually already says constant velocity, but also a straight line position time graph means it's a constant velocity. But the question is, will it be a positive velocity or will it be a negative velocity? Based on your position time graph. So your position time graph is going upwards. So will that give you a positive constant velocity or a negative constant velocity? Yeah, positive. Yeah, because your final position will be bigger. Say if this is, for example, your final position, and say this is your initial position, your final position will be bigger than your initial position. So if you subtract those two, you'll get a positive number. Okay, that will give you a positive velocity that is constant. This is zero. That's the 0 point, and anything above zero is positive. Right, and then how would the acceleration time graph look like? If your velocity is constant, what would be the acceleration for a constant velocity? So acceleration is the change in velocity over the time it took to make the change. Yeah, good, Keelan. It will be 0. Yeah, because from your velocity time graph, you can see that your velocity is constant, meaning it's the same all throughout. Your final velocity is the same as your initial velocity. Your velocity is not changing. And since acceleration is defined as the change in velocity, because velocity is not changing, acceleration will be 0. So velocity is not changing, it's the same. So Vf is equal to Vi, and acceleration will be equal to 0. There's no change in velocity, hence no acceleration. So let me just label this: acceleration meters per second squared and time in seconds. Right. Okay, and then I will let you play with the moving man. We can actually just look at that in the moving man simulation, right? If you move the man with a constant speed, all the way up there. Yep, you see how the position time graph is roughly a straight line graph. Okay, I was not so good in moving the man. If you're accurate enough in moving the man, then you'll see the position time graph is a straight line graph going up. The velocity is some positive number. We can enlarge that a little bit. Okay. It's a positive number, positive velocity that's constant. It's roughly constant, but there's a lot of uncertainty or variability because my position time graph is not so good. But roughly, you can see that the velocity is roughly the same all throughout the motion. And then you can see the acceleration, the green graph here, the acceleration is 0 because your velocity is not changing. Okay, so you can actually, yeah, you can use the moving man simulation to simulate such movement. So yeah, I'll let you play with the moving man simulation following the steps in the worksheet. And if you want to look at the explanations, they will be on stream as well afterwards. So are there any questions about the worksheet or the lab or the lectures that or anything we've been talking about today? None? Okay, I'm just watching the chat to see. Yeah, but there seems to be no question in the chat box. You have one lab every fortnight. So so the first lab is now available, but it's not due until the 3rd week, which is 20th of March, and then the second lab will be 2 weeks after that. So so you only have a total of 6 labs for the whole semester. Yeah. Cool. Yeah, that's strange because in my timetable I actually asked to remove that lab slot. Is that the Thursday that's showing in your timetable, Peter? So I'm pretty sure I asked the timetabling office to remove the labs from the timetable. So yeah, we won't have the in-person labs, unfortunately, just until from today. Oh, the one from today, the 1 to 3, yeah. So the 1 to 3 in QB5, those are that's the drop-in session. That's the face-to-face review workshops. You're correct. That used to be a face-to-face lab. But because we've moved the lab online, we've converted that lab to a face-to-face review workshop. So that's in QB5. It's a lecture theater instead of a lab room. So that will be like a drop-in session where you can go there and ask questions from previous week's materials. That will start next Friday, next week. There's no drop-in session today, just in case. Yeah, that will start next week. That's when you can go there and we can interact face to face. We can discuss any questions that you have from previous week. So take notes, a review workshop, and those will happen every week. Yeah. So the Manawatu, the Palmerston North review workshops, they will have them fortnightly every 2 weeks. But for us in Auckland, I've decided to have that every week, just because it's hard when you have many things piling up. So I want to clarify any questions you have on a weekly basis so that you won't get overwhelmed. So we'll have those every week, but we will start next week, just so that we have enough material that we've covered for the revision. All right, good. I hope that clarifies things. I'll send out a reminder email on stream about the review workshop starting next week, just in case. Don't want anyone turning up there today and then there's nobody there. Yeah, but cool. All right. So if there are no more other questions, then we can call it a day for this session. Just trying to speak slowly in case some question pops up in the chat box, but there seems to be nothing. All right, so then I'll see you next week on Wednesday for our next lecture. Have a good weekend, everyone. Take care and keep well, and have a good weekend. Right. Recording will be on stream shortly. So yeah. Thanks, everyone.